Welcome to a refresher lesson for rational exponents and radical functions, properties, and operations. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So in order to deal with rational exponents and radicals as functions, we first need to understand how to deal with them as expressions. And so we are going to spend a lot of time today with simplifying and adding, subtracting, multiplying, dividing, just kind of knowing how to work with these kinds of expressions and using the properties properly to help make our work a little easier. So let's start with simplifying radical expressions. First thing you need to know is that there's a bit of a difference between simplifying an even root and an odd root. So if you're going to take the root, nth root is how we usually say that, and your n is odd, and we call that n the index. So the index is this number right here. So if that n is odd, then the nth root of a to the n power is a. That's kind of the definition of what roots are. With n being even, we have to be a little bit more careful because it's really going to result in the absolute value of a, meaning that we are only ever really interested in the positive result of what that even root is going to be. So if we take the square root of 9, we always say the answer is just 3. We don't say it's plus or minus 3, or we don't include the negative 3 in the answer. Now you're going to see in my examples that I have actually written absolute values in the results when we have even roots. Depending on your teacher or the textbook that you're using, it might just be implied or understood that if you're using an even root, you can just write a, whatever that root is. And as long as you're only giving the positive principal root, is what we sometimes call it, you don't have to put the absolute value signs around it. So just follow the instructions that your teachers are expecting. Okay. A simplified radical expression is one in which you have no factors of m to the n power in an nth root of a. So if you can break your a down into factors, and you can come up with a factor that is something to the nth power, depending on what that index again is, then you need to take that out in order for your radical to be considered simplified. Okay. Some properties that you need to know in order to simplify things. There's the product property of nth roots. So if you're taking the nth root of A and the nth root of B, and those are real numbers, and you're talking about an n value that is greater than or equal to 2 and is an integer, then we know that taking the nth root of a product is the same as taking the nth root of each factor separately and multiplying that together. And vice versa. If we have the nth root of two numbers being multiplied together, we can combine those two radicands into a single product and take the nth root of the whole thing. Similarly, you can do this with quotients as well. You can take A divided by B, take the nth root of that whole fraction, or you can take the nth root of the numerator and denominator separately. And if you have the nth root of two numbers separately, in the numerator and the denominator, you can rewrite it as the nth root of a single fraction. So you can go back and forth with these. In this case, we have an additional condition that b cannot be 0 because b represents our denominator, and we don't want denominators to be 0. All right, so let's actually look at a few examples for simplifying radical expressions using the information and the properties we just talked about. So if I ask you to write or simplify the square root of 98, what you want to think about are the factors in 98. Now, there's a couple ways you can do this. Some people will think about it in terms of trees and just kind of splitting them up into what the factors might be and continuing on until you get enough information to tell if you have a perfect square or not, because this is a 2 technically for an index. For other people, they'll do what's called inverted division. And so you would start with your 98 and use an upside down division sign. And then you only divide by prime numbers. And you keep going until you get a result of 1 down at the bottom. And then you take a look at these factors that you get, and you look to see if any of them are used a number of times that works with the root that you're using. So in this case with the 98, it might be just as simple to think about 2 times 49 and realize that 49 is a perfect square. And so that means that we're going to rewrite 98 as 49 times 2. And then using that multiplication property that we just talked about, we can separate square root of 49 and square root of 2. And then we can go ahead and simplify the square root of 49 into 7. The square root of 2 cannot be simplified any further. And so 7 root 2 would be the simplified version of the square root of 98. Now we can do this with any roots. For example, if we have the cube root of 80, in this case, I may want to break this down a bit. So I'm going to use inverted division. And 2 is always a nice, easy prime number to divide by. So I'm going to do that for as long as possible. And then I get a 5. So I can divide that by the prime number of 5 to get down to 1. So now when I look over here at my prime factors, I can see that I have 1, 2, 3 2s. And then I have this 2 and this 5 that don't have enough to be cubed. So if I think about what's going on here, 2 cubed is 8. So I can divide this up into the cubed root of 8 times 10. The 10 is from our 2 and our 5 down here. And then again, we can separate those. So the cubed root of 8 and the cubed root of 10. And so now the cubed root of 8 will be 2. And the cubed root of 10 cannot be simplified any further. And that would be our simplified answer. Okay. Now, you can also simplify expressions that have variables in them. This is a quotient. And so when we're taking the root of a quotient, if possible, I would suggest your first step is to simplify the quotient itself as much as possible. You'll notice in the numerator and the denominator, we have some common factors like a 2 and an m. So I would cancel those out first before you actually deal with taking the roots. So we would have a square root of, so again, 54 and 196 share a 2. So this is going to be a 27. And on the bottom, we're going to get a 98. And then we've got the m cubed over m. So if I cancel out an m, I'm going to be left with an m squared on top and nothing on the bottom. And then we can split up and consider what is the square root of 27m squared and what is the square root of 98. Okay, so with 27, we know that can be divided into 9 times 3. With variables, we want the exponent to be divisible by the index. So again, if this is square root, our index is 2. And again, with 98, we just did that a minute ago. We'll make that a 49 times 2. So I tend to, in my next step, I combine the things that can be rooted into one radical, and then the things that cannot into the other. So the 9 and the m squared are both perfect squares. They go in one radical. The leftover 3 is going to go in a separate radical. Same in the denominator. The 49 will go in one, and then the 2 will go in the other. And so now the square root of m squared is going to be a 3m. And since this is an even root, we're going to make that absolute value of m square root of 3. And then in the denominator, square root of 49 is 7. And we've got the root 2. Now, again, your teacher might say that as long as we just all understand that it is the principal root of m, you don't need the absolute value sign, so just follow their expectations. All right, so what about rational exponents? Well, first of all, what are they? Rational exponents are just another way of writing radicals. So if you have an nth root of something, it is the same as saying that you're taking that something to a power of 1 over n. And you can expand on that by using any kind of fraction as your exponent. And so in this case, I like to say that if I have a to the m over n, I think of the fraction like a tree. And so the n in the bottom of a tree is where the roots are. And then the top of the tree is where the power is. So if you are talking a to the m over n, we're talking an nth root of a. The m then is a power. And you can either put the power after you've taken the root, which is what this part says, or you can take the power before you take the root, which is what this part says. Either one is fine. They're both equivalent. So it just kind of depends on the situation as to which one maybe seems easier. Okay. So if we're going to simplify expressions with rational exponents, if I'm taking 125 to the 2/3 power, I am saying that's the same as taking 125, taking the cube root of it, because this is the root, and then we're going to square that. So now you have to decide, would it be easier to square first and then take the cube root, or to take the cube root first and then square it? I would opt for taking the root first and then squaring. To me, that seems simpler. And the cubed root of 125 is 5. So then I can take 5 squared, and I get 25 as my answer. Okay. If I wanted to simplify something like -16 to the -3/4, we'll get to more of these properties in a minute, but maybe you remember that a negative exponent is the same as saying a to the negative b is the same as saying 1 over a to the positive b. So I'm going to have this negative. Notice it's not in parentheses, so that's going to be outside of what's going on. I'm going to take 1 over 16 to the positive 3/4 power. And then I'm going to take that denominator, and I'm going to think of it as the 4th root of 16, and then I'm going to cube that. So the 4th root of 16 is a 2, and then we're going to cube the 2, and so that's going to give us a negative 1 over 8. Okay? So that's how you simplify rational exponents. You think about them in terms of their radical equivalent. Now, as I mentioned, there are lots of properties of exponents, and I'm sure you have seen these before, so I'm not going to take time to go through each one. But if you need a little time to refresh, or if you've totally forgotten these, go ahead and pause the video right now and take a look at these and make sure you understand what each of these properties are, because they're very helpful when you're working with exponents. All right, so if we continue now, excuse me, as we simplify some more kinds of expressions. Our expressions can get a little bit more complicated or complex, and we just need to understand how to use the properties to help us get through it. So here I have 32 as a factor, and that's being multiplied by this x to the 1/3. And our property says that I can take this 3/2 and I take each factor to that power. So I would have a 32 to the 3/2, and I would have x cubed to the 3/2. Okay. So if I take 32, I'm looking at the, you know what? I think I have a mistake here. This is supposed to be to the 3/5. So let me change that really quick. There we go. So if this goes to the 3/5, and this is to the 3/5, then we're taking the 5th root of 32, and then that is going to get taken to the 3rd power, and we're going to have x to the 1/3 to the 3/5 power. Now here, the 5th root of 32 is a 2, and then we're going to cube that. Here, since we're taking a power raised to another power, that means we need to multiply our two exponents. So we'll have 1/3 times 3/5. The 3's are going to cancel out, and we end up with a 1/5. So this is going to be x to the 1/5 power, and then our 2 cubed will become an 8. So 8x to the 1/5 is going to be our final answer. And that all comes from just using those properties back on this previous page. Okay, let's take a look at another one. Now we've got a quotient with lots of different pieces being raised to several different kinds of exponents. So let's take a look at this one. Now you can kind of choose the order on how to do some of these things. You could simplify everything inside of the parentheses first, because you can see there are multiple x terms, multiple y terms. So you could simplify all that first and then deal with the 1/2 exponent. Or you could go ahead and take every factor in the numerator and the denominator to the 1/2 exponent and then do the simplifying. Either way would work. So again, choose whichever way makes more sense to you. For me, I think I'm going to simplify that inside first. So I'm going to have a 16 for my x terms here. Try that again. So for my x terms here, if I'm going to divide powers, that means I need to subtract the exponents. So I have x, the 4/3 minus -2/3 is going to give me 6/3. And then my y terms here, same thing. If I have y to the -5/6 and then y to the 1/6, I have -5/6 minus 1/6, which is -6/6, which means that I'm actually going to want to put that in the denominator so I can make the exponent positive. And so now a little bit of simplifying. We've got x 16. X to the 6/3 is x squared. And then y to the 6/6 is really just y to the first. Now remember, all of that is still being taken to the 1/2 power. Okay, so now we take 16 to the 1/2 power. We take x squared to the 1/2 power. And we take y to the 1/2 power. So the 1/2 power is really just saying square root. Excuse me. So square root of 16 will give us a 4. X squared to the 1/2. Again, we multiply our exponents together and we just get x. And then our y to the 1/2 in the denominator. And this would be our final answer. All right, what about some adding and subtracting? Well, if we're dealing with radicals, you can only add and subtract radicals if they are like radicals. It's kind of like what we used in polynomials when we talked about like terms. A like radical is a radical expression with the same index and the same radicand. So remember, the radicand is what's inside of the root sign. So the index and what's inside of the root has to be the same in order for you to have a like radical. And when you're going to add and subtract, only the like radicals can be combined. Okay? So if I am looking at a problem like, I want to simplify the cubed root of 128 plus the cubed root of 54. So for the cubed root of 128, I can think about the fact that I've got the cubed root of 64 times 2, and I've got the cubed root of 27 times 2. Okay, so if I split these up, cubed root of 64, cubed root of 2, cubed root of 27, cubed root of 2. The cubed root of 64 is 4, and the cubed root of 27 is 3. So now I have like radicals because both terms have the third root, cube root, of 2. So I've got 4 of those cube root 2's in the first term. I've got 3 of those cube root 2's in the second term. I'm adding those two together, and therefore I end up with 7 cubed roots of 2. Okay. And again, your expressions could have variables in them. And so if I'm looking at this problem where I'm simplifying 9 square root of 50m squared minus 6 square root of 32m squared, at the moment, I cannot combine these because what's inside of each of the square root signs is not exactly the same. But neither of them is completely simplified either. So I'm going to go through that first. Square root of 50 can be broken up into 25 times 2. The square root of 32 can be broken up into 16 times 2. So now we're looking at the square root of 25 times the square root of 2 and a square root of m squared. Here I have a square root of 16, a square root of 2, and a square root of m squared. So we'll have 9 times 5 times the absolute value of m, and then the root 2. Here we'll have a 6 times 4 times the absolute value of m times the root 2. So we've got 45 absolute value of m root 2 minus 24 absolute value of m root 2. So we have like radicals. We also have like terms in that they're both dealing with absolute values of m. And so now it's just a matter of taking our 45 minus 24 to get 21 absolute value of m root 2. Okay, so that's adding and subtracting. What about multiplying? Well, we already talked a little bit about that product property for radicals. And so when we use it on something that's a little bit more complex, we just have to remember that numbers multiply with numbers. So the 10 and the 4 get multiplied together. And radicals get multiplied with radicals if they are the same index. So we're going to have 10 times 4, and then inside the radical, we'll have 6p cubed times 3p. Okay, and notice that I took these two separate radicals and I combined them into one radical. So now we've got 40 on the outside, and we've got a square root of 18p to the fourth on the inside. The 18 can be split up into the square root of 9 times 2. We split those apart. We've got a square root of 9, a square root of 2, and a square root of p to the fourth. So the square root of 9 becomes 3. The square root of p to the fourth becomes p squared. Now, it's not necessary to put that in absolute value because the squaring already makes it positive. So the absolute value signs are not necessary in this case. And then we still have that root of 2. And so our final answer is going to be 120 p squared root 2. And that's usually the order that these kinds of expressions get written in. You have the number first, then you have any of the variables outside of the radical, and then you have whatever is inside of the radical. Okay. Let's take a look at this possibility. We've got 2 fourth root of 20y squared times 3 fourth root of 28y cubed. Now, in this case, if I use the same process that I did in our previous example, I'd be taking the 2 times the 3. That makes sense. But then I would be trying to take a 20 times a 28 and then taking the fourth root of that. And that sounds like it's going to start to get kind of difficult and messy. So one of the things you can do if numbers start to get a little bit bigger is you can take your 2 times 3, okay, take those two, but then inside of your radical, instead of writing the product of 20 times 28, actually break down the 20 and the 28 into prime factors. So for 20, we would have a 2 times 2 times 5. For 28, we would have a 2 times 2 times 7. And then we would have the y squared times the y cubed, which means adding exponents, and we'd have y to the 5th. Okay? And so what we're looking for is any factor that can be used 4 times, which we have with our 2's. We've got 4 2's here. So when I go to combine things, in the radical that I can actually simplify, I would have 2 to the 4th, and I would have y to the 4th from this y to the 5th expression. In the radical that I cannot simplify, I would put the 5, the 7, and then that extra y. So if we simplify now, the 2 times the 3 gives me a 6. The 4th root of 2 to the 4th will be 2. The 4th root of y to the 4th is going to be absolute value of y. And then we'll have the 4th root of 35y. So last step, multiply our 6 and our 2 together. We've got 12, absolute value of y, 4th root of 35y. Okay. One more example. This is a case of multiplying with radicals involved, but we're actually multiplying what looks like binomials. So we've got 2 expressions where we're adding or subtracting the radicals, and then we're multiplying those 2 expressions together. So we can still use FOIL, like we've used with our quadratics. And so our F would be taking the 2 root 2 times a root 2. Our O would be taking 2 root 2 times 4 root 5. The I would be the negative root 5 times the root 2. And our L would be the negative root 5 times the 4 root 5. So if we take root 2 times root 2, we're going to get a root 4, which is just 2. So F is going to give us 4. In the O, we're taking the 2 times 4 to get 8. And we're taking the 2 times the 5 inside the radicals to get 10. For the I, we've got a negative, and then the 5 times the 2 inside the radical gives us 10. And then for L, we've got the negative 4, and then the 5 times 5 gives us 25. So negative 4 times 5, which is negative 20. So if we put that all together, negative 20, there we go, sorry. If we put that all together, we've got 2 terms that end up just being numbers, and 2 terms that are not only radicals, but they are like radicals. So we should be able to combine those. So the negative 20 with the 4 gives us a negative 16. And the 8 root 10 with a negative 1 root 10 means you're going to end up with a 7 root 10. So that would be your solution. Now, for dividing radicals, we've already seen the quotient property. And so because of the quotient property, when I am dividing two separate roots, like these cubed roots, I can always put them back together into a single fraction if that's helpful. And in this case, I think that is helpful because of the repeated variables and the common factor of 2 that we have. So by putting them together into a single fraction that we're taking the cubed root of, that allows me to do some simplifying before I have to take the roots. So the 250 divided by 2 will leave me with a negative 125. Then I've got an m on top with a negative, m on top with m to the negative 2 on the bottom. Subtract our exponents, we get an m cubed. And then I've got n to the negative 2 in the numerator over n to the 4th in the denominator. And so that's going to give us n to the negative 6, which I will put in the denominator to give me a positive 6 for the exponent. Now I can go back to taking the root of the numerator and the denominator separately. Okay, and then we simplify from there. So the cubed root of negative 125 is actually a negative 5. The cubed root of m cubed will be m. Remember, we don't need absolute value signs when it's an odd root. And then the cubed root of the n to the 6th will be n squared. And so this is your result. Now, one final thing about simplifying radical expressions. A simplified radical expression is considered to be one where you have no factors in the radicand that have perfect powers of the index. So you've done any simplifying of the roots themselves. You have no fractions in the radicand, so you've separated those out. And you have no radicals in the denominator. If you end up with something where there is a radical in the denominator, then we need to do something called rationalizing the denominator, which is a process of converting a fraction with a radical in the denominator to an equivalent fraction whose denominator is an integer. Now, how do we do that? Well, it partly depends on what you start with. If you start with something like this, you have 1 over square root of 5. Our goal is to change our square root of 5 into an integer. And so we want to multiply by something that will create the square root of a perfect square. So if I'm starting with a square root of 5, I would want to multiply by a square root of 5 because that is going to give me a square root of 25, the square root of a perfect square. But because I want to keep all of my fractions equivalent, if I multiply my denominator by a square root of 5, I also have to multiply my numerator by a square root of 5. So 1 times the square root of 5 will give me a square root of 5 in the numerator. And then I take one more step to simplify this square root of a perfect square, and I end up with the square root of 5 over 5 as my rationalized answer. Having a square root in the numerator is okay. It's when it's in the denominator that it's not considered simplified. Now, what if it is a cube root or some other root that's in the denominator? Well, then the idea is the same. We want to create a situation where we have the cube root of a perfect cube. So if I'm starting with a cube root of 1, 2, what would it take to get the cubed root of a perfect cube? Well, I would need 2 more 2's to get the perfect cube. So I would want the cubed root of 2 more 2's, or the cube root of 4. And that's going to give me a cube root of 8 in my denominator. But again, if I'm multiplying by a cube root of 4 in the denominator, I need to multiply by a cube root of 4 in the numerator as well. And so 1 times that cube root of 4 becomes my new numerator. So now when I simplify my denominator and take the cube root of that 8, I end up with a 2, and this then is my rationalized answer. Now, there's one other type of rationalizing that you are sometimes asked to do, and that is when you have addition or subtraction in the denominator, and at least one of the terms that you're adding or subtracting is the square root. Now, this only works with square roots, okay? This isn't going to work with cube roots or fourth roots. But if it is a square root, the trick in this case is to multiply by the conjugate of the denominator. Now, you might remember conjugates from our complex numbers. A conjugate just changes the sign that's in between the two terms. So if we're starting with 2 minus square root of 3, we're going to make this a 2 plus square root of 3. And again, what we multiply on the bottom, we have to multiply on the top. So now we're going to multiply this out. On the top, we're taking 5 times 2 plus square root of 3. On the bottom, we are going to be taking 2 minus square root of 3 times 2 plus square root of 3 and FOIL it. Okay, so distributing the 5 gives us 10 plus a 5 root 3. If we use FOIL on our denominator, we've got 2 times 2 plus 2 times root 3 minus 2 times root 3 minus root 3 times root 3, which is root 9. Now notice what happens. Positive 2 root 3 and negative 2 root 3 cancel out. That's what multiplying by the conjugate does. It makes the outsides and insides cancel out. And so what you're left with then in your denominator is this 4 minus the square root of 9, which is 3. And since that is just 1, our answer is just 10 plus 5 root 3. Okay. All right. Well, I hope you found this helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.